Okay, so exercise solutions and recording. So so we had this differential equation problem, and just reminded that if we would have here the capacitive part, which would be plus 1 over c to the integral of I dt, then especially for 10 we would need to use the integral equation part, but this doesn't happen because we don't have a capacitor here. Anyway, capacitors in a direct current circuit would be a bit odd. So now we can just deal with the regular terms and get rid of this constant here, so that we don't need to go to non-homogeneous parts. Then we do have the option to differentiate once. So then we have equation of this form. We divide by L. Well, that's not, strictly speaking, not necessary, but it makes it nicer to handle this equation, and we get those. And actually right here, we could already, on the characteristic equation, because C is 0, we do already see from these multipliers that what kind of a form it will be. I have here used the full formula, good to practice as well, but alternatively, we note that the characteristic equation is, so we had that's an AR squared plus BR plus C, which in our case is R squared 10 plus 10R, which is, if we take R as a common term, that's R plus 10. So here we already can directly see that the roots of this for the R are 0, so which makes this go to 0, or minus 10, which then makes that part to go to 0. In any case, we got the equation. Now we're trying to figure out, well, there's 0, so 0 times anything is 0, and e to the power of 0 ends up being 1, so we get just a to e to the power of minus 10t plus b. And then one way we know that it approaches u equals ri is that, well, we know that this kind of form of equation does approach a certain limit asymptotically. And if we know that it approaches the limit asymptotically, if we go really back here in the beginning, when change is 0, and anything that's left is u equals ri. And at 0, before we flip the switch, we do have no current at all, so it must start there. Using this information, we can then fix the conditions. So the condition that at 0, this must be 0, we get the result that a equals minus b, or b equals minus a, whichever way you want to do. And then when the other part goes to 0 as time goes to infinity, this is a property that exponential functions explode really fast, and when you get it shows in the denominator, so negative powers, then the usually whatever we do have in the numerator, it doesn't matter, the quotient goes to 0 relatively fast. So b must therefore be the value which this approaches, and because a was minus b, we get the a value fixed there. Okay, critical damping. So we have 4 cases of oscillation, and this is one of the physical examples of what we could use this kind of a differential equation. And so pendulum models, in case of a pendulum, then the dampening force is air resistance typically if it's in air or other fluid, or spring and mass, which actually in our case it does have a spring, so it's some kind of a spring mass dampener, mass spring dampener system if we go in order. So inertia is relative to acceleration there, so force of inertia. Then we get the damping force, which is this drag force relative to velocity, which is the first derivative, and then the spring force is relative to location. So the further we stretch the spring, typically the more we get force. Of course, there are some assumptions like the spring is massless and other minor things. But usually when we're having the spring and mass systems, then the mass is relatively heavy compared to the spring. So acceptable simplifications. Sum of forces are 0, and which model matches which? Okay, harmonic oscillation was so there are videos on Moodle. Harmonic oscillation is a case where the oscillation does never go down. And yes, was the question, does it really happen in nature? Well, on the macro scale, no. At least I can figure an example. Maybe if you had some kind of a system going on space, rotating something, then maybe that might be some kind of a harmonic oscillation on the orbit. But in real case, even that, you're going to have a passing other celestial body that has a force of gravity on that which disturbs the system. So in practice, not really. Maybe in electronics, but then we're feeding in extra energy, so that's not a pure harmonic oscillator either. But for example, some stuff in our mobile phones, for example, typical mobile phone accelerometers are actually working with oscillation. So there's a small oscillating part, and by measuring how it changes, then we can figure out how, for example, which way the accelerometer goes, and also some clock path in, for example, iPhone. This is the reason why there's a notation. If you ever read the proper iPhone manual, it says that you should not use your iPhone in places where there's significant amount of helium, because the oscillator is a mechanical system, electromechanical system, really small one, and helium has these nice properties that it's not a loaded, it doesn't really react with other substances very easily, at least to form molecules. It's really small, and it's not electrically charged. So the helium atoms will be able to go through the seals used in some mobile phone oscillators, and then they do still have mass. So then you're having extra mass ping-ponging inside the oscillator, which will set off the mobile phone clock. But unless you're doing something rather unusual, like servicing an MRI machine that has a leak, then that probably shouldn't matter for mobile phone users. But such things happen. Yeah, we were on the actual spring mass dampener example. Yeah, harmonic oscillation, completely undamped system, so we know it's a pure sine wave solution. And in the case we do get that is when the discriminant is complex, and then we do have no other factors there. So our roots go to zero otherwise. So the real part of the roots is zero, and we do have an imaginary part, then we have harmonic oscillation. If we do have the real part, then we do have this e to the power of something x or something t, and that will act as the upper limit of oscillation, and the oscillation will then be dampened. So we're having 10 dampened oscillation, and that, of course, mathematically, it is fully dampened at infinity. In real case, we're probably going to have other friction forces acting on it, and it will be eventually stopped. And if we start from the zero damping, we get a harmonic oscillation case, and then we start increasing damping. We'll go to eventually find a value where the discriminant is zero. We get this equation. At the discriminant equals zero, we do get this kind of a critical damping part. We can see that when we increase the damping ratio, it takes further for it is really easy if you have a plotting calculator or can use a computer to plot. So you can see that the time it takes to go into smaller oscillations increases because the dampener would be then slowing down the oscillation speed, and therefore increase the time of the oscillations, and then it takes more time to get to those low values. Actually, it won't oscillate with overdamp, but it will take a long time to get to zero. So if you ever need to, for example, design a shock absorber, you should be looking at harmonic, not harmonic, but you used to look at the critical damping and then maybe a little bit of extra damping just in case someone decides to do something odd. And we can solve that from the discriminant equation. So discriminant equals zero, we get b squared is 4km, or b equals square root of 2, square root of 4, which is 2, times square root of km, which in this case is this square root of 5,000, or if we flip this around, we should get to something like what was on the hint sheet. Okay, so we had a simple integral question as the final question. So we're having no simple zero finding question. So find the zeros of the derivative, and also remember check the endpoints, because in this case we had the highest value at the endpoints. So we could do it like this, so convert to acceleration first, or we could first do the force and consider that the maximum acceleration must be at maximum force. And we can take a common term, so we can then integrate only the slightly easier part, solve roots for that. So where we did these derivatives, so we find the zeros of the derivative, which are the roots. We note this is one possible use if we can model something as a polynomial, and then we can relatively easily find roots, or if we just find any function and then use the numerics to find the roots. So that's one use in optimization. So solving roots, and we can solve values. One of the roots of the derivative is negative, out of bounds. One of the roots is positive. We can check the value. And at 0, which is the one endpoint, we had force value of 64, and it's going up the further we go negative, so that is a maximum. At the root, we had 57.3, it's 0. It was going up on the other side, so this looks like it will be either a minimum or saddle point. Let's see. On the other side, well, it's a parabola, so we know it's actually now a minimum. At the other endpoint, it was 80, which is our maximum value, and it's also going up. So yes, we know that the minimum is there, and the maximum value, based on the looks of what the force is at the endpoint t equals 1. And with the force of 80, and we had a mass of 10 kilograms, and we have acceleration of 10 meters per second at time of 1 second with the given force impulse. This is a bit funny in part because digitally cut from maximum value to 0, but that's a somewhat of a textbook example with a minor connection to reality. So need to think about what actually a derivative is. Okay, then to our current part. Sorry about people being remote because we are not having those slides yet. There may be some errors, so I'll want to upload them after the lecture, and also get, I think the previous lecture isn't yet online. I'll need to get that video, and then I'll probably want to do some extra examples here as well. I do have a few, but there are a few of those that are still missing from the slides. So last year I was doing mostly on the board. And now I want to duplicate the slide, so that way. Yeah, we just did see the solution for differential equations. Areas of plane regions. Okay, so now more of these area calculations. Last week on the numerical analysis, we already talked about this a little bit. So how to calculate areas, and let's have a look at the theory. I probably should have done this before that, but integral and area. Now we could consider the area integral is the area where the function is positive minus the area where the function is negative. If we call those A1 and A2, we do see that the integral of the absolute value is the sum of these areas. Here we get the triangle inequality, that this is always larger than or equal to the integral. The useful rule here is that the integral of sums is the sum of integrals. So we can either integrate separately and then calculate those areas, or then we can combine those, calculate the combined function, and then integrate that, whichever is easier. And if we consider, now I'll need to minimize this to see completely. So as long as f is smaller than g, we might consider this the height of area times the width of area element. So we get surfaces here. And in more general, then we need to take the absolute value in case these functions do change places. So at some point, we're not having the nice order that g is greater or equal to f. Now let's have a few examples. And now typically when you're asked an area between two curves, if you're not given limits, then the actual question is that find where these intersect. I'm gonna be slightly lazy. That's why I, in the beginning of the lecture, launched MATLAB. So I'm gonna start plotting these. So first one is x squared minus 2x. Where's MATLAB? We're having here. So we're having a f1 equals x squared minus 2 times 2 times x. And our function 2 is just the inline way of doing functions here. Four minus x squared. Now this will be incredibly small for people onto net, but it allows me to put this side by side. So plotting here pretty often helps. We can clearly see that we're going to have when we do f1 minus f2, we're going to, if we go by that route, we're going to have minus minus here. So we're going to have 2x squared minus 2x minus 4. So we could solve that. But let's see some plots. So f plot f1. We're having that kind of function. Hold on, which tells me that don't overwrite the previous plot. Tells MATLAB that. So we do get two intersections there roughly at -1 and 2. So now we do have an integration limits. Usually you're supposed to do this analytically, so but we can then find, and actually f2 is larger here. So we're gonna tell that we're gonna I actually need to remember what the syntax for this was. So there's we have, if you want to check numerical integration results, well, you can do that with this command, which is relatively good on quadrature. So a1 is integral f1 from -1 to 2, really small. A2 is integral of f2 from -1 to 2, quite large. And then area is a2 minus a1, because our first function, which was plotted here in blue, is smaller. And now we're seeing that this is actually a nice little notation. And now we went beyond the numerical accuracy of the system, so it suggests that that a2 minus some small number minus some small number is a2. So now we actually went past the limit of this system. Is my f1 correct? Yeah, CFP so. Yeah, so -1 is 1, should be -1, and 2, and yeah, integrals this, yeah, should be something like that. Okay, sines and cosines slightly more varied, so we get f1 equals x. This one was a simple one, as is the other. F2 is at x cos x, a equals 0, b equals 2 times pi, and we can still plot those. F plot. I need to put hold off now so it doesn't keep the old ones. So F plot F1, A to B. And now it's somewhere here. Yep, that looks like a sign. Hold on. F plot F2 from A to B. Okay. And yep, that was a cosine. So yeah, there's a typo. With computers, need to be quite careful because they usually don't ask you, wait, what's that? That's dumb, and is that really what you meant? So hold off again. Now I'm gonna pick these plot commands from here. Actually, I can just paint the whole thing and rerun. Okay, now we're looking at the area between these, and there are a few ways of doing this. One would be that we would solve the intersections and then integrate bit by bit to find the area. Or maybe I'm going to be a bit lazy here. I'm going to tell that we do have a function of x, which is absolute value of f1x minus f2x from A to B. And that gives us an estimate of the area. This is probably something that if we, well, not quite, well, might be a fraction of pi. So I'm not sure if this is a rounding error here. But the same thing also applicable in pen and paper, because now if we're having sine minus cosine, there's probably in textbooks there is a formula that tells that if we have sine plus cosine, we get something. So we might be able to manipulate that into a nicer form. I should memorize some of the easiest ones, but to be honest, I'm quite used to using textbooks in these cases. So I haven't really memorized most of the formulas. And here's one interesting thing. We're getting x as a function of y. And those go exactly the same as a regular integration. So it doesn't matter if we have flipped the axis around. So now we're just integrating not dx's. We're probably easier to do this by integrating dy's. And this is probably even easier to just do absolute value of y squared minus y minus 12, find the roots, and integrate. It's going to have 2 roots, and that way. Let's have a quick look how it looks like. So now our f1 equals fy minus 12. Our function 2 is, well, this is a bit dumb because it's just y. out of f plot f1. Did we get something here? Yeah, just a regular parabola that has a minus 12 at what we know. So the constant tells what's the value at 0. Hold on, f plot f2. So what's this area? And the intersections are somewhere around 3 and probably 4. Roughly so. Really hard to get that fixed here. So if we're doing integral at x, f2 is now the larger one, 2x, well, absolute value f2 x minus f1x. So I redefined a new function to fly from minus 3 to 4. We should get a volume. This is quite often how it goes. If we can define a function, then as long as we're not getting something funky with the rounding errors, which I did get at one point, then we usually can do these numerically. This is integral is, to my understanding, using a slightly adapted form of the Simpson's equation or Simpson's method. So the basics how to do those in a semi-visual way. We can do the similar things by solving these analytically, or then just combining the functions and then integrating a resulting function instead. But then integrating an absolute value function is occasionally annoying. And then one trick, this is one of those doctors hate this one simple trick kind of things, so which can make also integration easier if you have a function that is hard to integrate, which is integration by parts. Now the question is, anyone heard about this before? Okay, some. So we do have this general formula that if we have well, where it comes from. So if we do the derivative of this, so it is just a product rule, so we can divide it that way. And if we now consider that, solve that for the part where we have u and take an integral, we should get something like this. So essentially integrate the product rule and you get this rule for integration by parts. So the general pattern here below is that if we have some function u, which is easy to differentiate but hard to integrate, and we can somehow divide it so that we are having a part we can easily differentiate and then something else. We do know that this, by the product rule, in differentiation, this part is equal to this kind of a multiplication of these functions. Hopefully this part that's left is easy to integrate, so we can integrate that, and then second integral of that times the derivative of u. So if we have a part of an equation that's really hard to integrate, and it has an easy part to integrate, then we can swap these around. Let's have a few examples. Those are the easy ones. So one is this x to the power of ex. I'm not sure if there's a general rule, and then the opposite, that maybe we're having a logarithmic function. So this one's easy. So our easy part here, well, this is kind of a funny that way, but we do know how to integrate x, but we can still divide it that way, because here we do get this trivial part that the derivatives and integrals of each part of x are itself. When we plug those in, we get that this integral is, well, itself minus something extra. Well, integral of well, the derivative of x is a constant, so we just get the integral of ex left plus c. Remember, there's an integral step, so we in this case didn't want to start integrating ln x, but we need to, because that's the only thing left. But we do remember that it does have an easy derivative of 1 over x. And then when we have the differential unit, it's dx as well. The trivial part, if we have the dv is just dx, then v is x. We plug this in on the formula. So uv is x ln x minus integral of v times du. Well, now here's the nice part, that integral v times du is x over x dx, which is constant dx, and if we integrate a constant, we get just x. And we already, because this happened to be the logarithm function, we know that x must be greater than 0, so we don't need to consider. Otherwise, if we get x over x, then we need to remember to carry the part where x cannot be 0. So we cannot skip that over, or we get all kinds of funny proofs, so to speak of. So I just did the air quotes because I'm not in front of the camera. Like 1 equals 2 is possible to prove if you skip over the part where you occasionally had a divide by 0, which of course it cannot be allowed to happen. In general, that's actually a logical rule. If you somehow in your proof have a contradiction, then from contradiction you can derive or kind of then have anything if you have a proof where a contradiction is true. But we need to have some background on logic before going through that. General advice. So if you have a polynomial in your integral, so a power term multiplied by exponential signs, cosines, then you typically do the integral, divide the integral so that your u function is the polynomial, and then dv is more or less everything else in the part. So that's what we did. That's why we divided the x times ex that way. If we have hard to integrate parts of logarithm, inverse, trigonometry, those are typically hard to integrate, but we know the derivatives. Then put the hard parts in the u and everything else in the dv. So then we don't need to integrate the u part, we just need to know what is derivative, and then the dv part, which hopefully is easier to integrate, we can then integrate it twice. So we are swapping one hard integral into 2 easy integral steps. If possible, divide and conquer, so do it bit by bit, because occasionally everything else is slightly complex. How would you divide the first one of these? So u equals what? someone side at least. It not said something. So x squared, and then the dv is sine x. First integral of sine x is minus cosine, and then minus cosine we need to integrate, which goes to minus sine. And then plus some c's technically, but those cancel out usually in the formula. Same here with tangent. Now we probably want to grab the arcus tangent as the stuff we really didn't want to integrate. So we calculate its derivative, which is 1 over 1 plus x squared, if I remember correctly. And then we integrate x. And if I remember right, that formula we need to do a few times. And same with the arcus sine. And with arcus sine x, we again probably here have just the dx as the dv part. All right. Okay, that was it for today. I should have more time today to have a more detailed look at these examples, which will help. At least the first one is slightly annoying. You need to actually use the integration by parts rule twice to get a nice answer with no integral signs. But I'll get examples done and we'll continue tomorrow. You should also get some more homework today, which is mostly textbook stuff, maybe something easy on this, and then more about the last week's integration stuff. Practice. And yeah, this is more or less it for today's lecture. If you have any questions, do ask. And if you don't want to ask now, you can also ask by email. Or, okay, you can actually post on the Moodle, but email works. And also I will of course have office hours, so those who cannot attend face-to-face teaching, then I do have office hours there, and I'm also on Teams, and a typical setup is a camera and marker board, so I can then at least draw something for you. If you can, for example, take a picture of what you have been working on your own pen and paper, or if you're working on the computer, then probably you can send that document as a PDF or something. But yeah, this is it for today, and see you tomorrow. I'll try to get the homework also done too, or homework problems defined today. Also done as well, so I have the solutions. And let's